All right, thanks very much. I'm Wes Hardaker from ISI, as I mentioned multiple times today. Thank you all for being here. You know, I was worried they put me in the last slot, and that either means that my content was awful and they said, just put him in the last slot, or I get to close the show down because I think you're going to like what I'm going to say. But I have to start with saying this conference has been perfect. The content's been awesome. It's run really, really smoothly. Can I get a round of applause for all of the conference organizers, please? So one of the things that we deal with is in operations all the time are how to figure out what's going on in the traffic that we receive, because we receive a lot of funky stuff. So I have been working for a little while about something I'm going to call traffic Taffy, because I just thought that was a cool name more than anything else. So as you know, network operators love graphs and we hate graphs, because at the same time we want to know, what are these things? We get all of these weird things. So this is a graph from Beirut a few days ago. And why do we have a big, a bunch of spikes? Those actually happen all the time at one Anycast instance. And we have this big, long, plateau. It's like, why do we have it? What is it? So the problem with, all of our current solutions is you run TCP dump, you run Wireshark, and then you look at it by hand, and if you're lucky, if it's a really big spike, it's really obvious, right? You're getting a ton of stuff to the memcache port. Okay, well now I know what it is. I can filter it out and deal with it quickly. It's very easy for huge spikes. It's a lot harder for secondary goals or secondary signals that are sort of buried underneath, and it requires a lot of knowledge of the protocol in the first place. There's some automated stuff. A lot of those, they're really only looking at what's inside the spike, and so it gives a lot of false positives, stuff that actually turns out to be normal. Now, you can't get rid of human expertise. That's just not possible. But I kind of figured there's got to be a better way, right? So for all your Friends fans out there, this is a Friends reference to Joey who couldn't open a can of milk. Carton of milk. So I wanted to reduce the problem space. I figured, in order to figure out what these things are, I really only want to figure out what might be causing a single change, right? So not more of the same, not, like hours later, I'm getting twice as much traffic because some continent woke up, right? That's just more of the same. I want to know something had to have changed to cause spikes, right? So my insight was, let's compare. Let's actually essentially do a network diff. So let's take a sample of traffic in the normal period and a sample of traffic in the weird period, and then look at the difference between them. So for the rest of these slides and in the tools, I call them left and right, just because I had to call them something. And it turns out that I'm comparing against time, I'm comparing against files, so left and right just seemed like the best thing I could do. I will note that right and left can be reversed. You can actually compare traffic after a spike too, if you just want to know what just went by. So my goal was, let's look for these single cause changes, find out what changed, find out when it changed, and then look at a delta in order to do that, right? What changed what was the summary between these two different things? What was in the regular traffic, what was in the anomaly traffic, and find the difference. And as I said, the tools actually work with, you can say, I have this file and that file, compare these two. And you can also say, things were changing over every second, compare every second against the next second. One of my questions that was going to be today, do you need something faster than a 1 second binning? Peter's already told me yes, because he has traffic that's actually smaller than a second. But you can filter it out using TCP dump too. So my approach was, let's do deep packet inspection, right? I don't want to try and figure out myself what to tell the tool to actually go look at. I want it to tell me what did it find. So I do deep packet inspection of sort of the baseline, and I do deep packet inspection of the anomaly, and I count every value for every protocol field. Now, so all the examples you're going to see today are DNS-centric, because you guys are all DNS people. This works for anything, not just DNS. It works for HTTP, it works for IP, it works for IPv6. But today is all going to be about the DNS. And then you sort and filter and report the events based on what you found. So there's a bunch of tools. I'm going to talk about the tools in a little bit later. But it's very easy to install today. It works today. You can do pip install traffic Taffy and you'll get the tools. It is, I'm going to call alpha software. And the reason I'm here is that I'm going to be working on this for the next few months fairly solidly. I want early feedback, right? I want you to tell me what's working, what's not working, so that I can actually improve it immediately while I'm developing it. So rather than giving you a finished product, it actually works and it's a whole lot of fun to play with. I want you to go ahead and start playing with it now and then give me feedback saying what doesn't work or what problem were you not able to solve. So I'm going to go into two case studies. The first one, these are both traffic from b.rootservers.net. And the first one is these three large spikes that we saw on our one Anycast instance. And they're not huge, but they're interesting because what are they? They have three large spikes and then they went away. Can we find the root cause? It was not easy to do by hand. So I threw it into Taffy compare, which is the first tool that I think most people will want to start with. You give it a left, you give it a right. I gave it a file in the middle of the spike and a file to the left. And then I looked at the output. So the output of Taffy compare gives you a colorized console result. So the lines that are in green values on the left are rising, the ones that are in red are falling. And it gives you 6 columns essentially. And it's the total count, in the left, the total count in the right, and the delta. I'm not going to talk too much about those. It gives you more data than you can possibly imagine for your expertise to look at. Most of the stuff that I'm going to look at today is the delta percentage on the right, which kind of tells you that between the left-hand percentage of traffic that actually had a CD bit, which is a checking disabled bit for DNSSEC, right? Basically, the total percentage on the left hand was 39%, and the total percentage on the right hand was 54%. So the 0 value went up, and correspondingly, the 1-bit value went down in these packets, right? So why? That's a whole different story. So let's go into the why. Right, so this is actually, again, the same thing. This is actually a screenshot of the entire screen. And I got lucky with this one, put everything right in one place, and there was no breaks in between, with other stuff that actually really didn't matter much. Of course, the tool's not perfect, so you do have to know a little bit about what you're doing. But let's break down what is actually on this screen. So first off, the very top one is a bunch of queue names. There's a queue names, and they're all number: all :443, right? This is clearly Docker port mappings that somehow ended up in DNS queries. Why? I don't know. They're coming from a lot of addresses. That's actually why the source addresses isn't listed. It's some cloud service that apparently blew it somehow. But they were all for A records, so there was actually an increase in a queue type of 1, which is looking for an A record. You can see that in the R code, because this is also capturing all the response traffic going back, you can see that our NX domain responses went up, so value 3 for the R code. One of the things that I would like to modify in the future of these tools is to give better human descriptions. I want to go pull all the IANA tables and actually give you, real values rather than 3 and 0. Again, this is an early version of the tool. The truncation bit went up because they hit our RRL limits. Right? They were asking so many questions about port that they actually hit our RL limit, and then we actually started returning truncation, and they had to come back over TCP. And then finally, this is all heading to our older IPv6 address, so it gives us a feeling for, we have now 3 addresses that we bind to, and this was running toward our older one. So as this is the second case study, and this is actually, I call it a large DDoS attack. It's really not that large. It didn't take us out or anything. But it was a decent amount of traffic. And we actually published this. So we actually published a lot of data sets of anomalies that we've seen that are large so that people can go look at them. And so you can actually request them from us by filling out a form. And so the only thing in our data set description, the only thing in our README is this is all no fixed query names in the traffic. It's all 554 bytes, so it's easy to filter, actually. And it's all randomized sources. And that's all that the README file says. So I ran Taffy traffic on it to say, hey, or traffic Taffy, I always get those reversed. And it's to see what's actually inside. Is there more than that? And so the answer is, of course, yes. So now you'll see that there's breaks in the data because there actually was some other things that really weren't as relevant that I filtered out. But in these, you'll note that the one thing to note is that I called it cache disabled here because I've heard it too many times, incorrectly. It's actually checking disabled. Warren spotted that the other day, and like 4 other people looked at this too, and they didn't notice it too, because so many people have called it cache disabled for a long time, and it was just wrong. Anyway, you can see that the cache disabled bit is essentially going, and it actually says increase there, it's actually decreasing. So the 1 bit is actually decreasing. There was an increase in the operation codes, the really weird operation codes, right? 7, 8, 14, 9, and 15. Those aren't real operation codes. You can see in the left-hand column, it's all zeros, right? There was none of those in the normal traffic, and then there was 200,000 of them in the regular one. This is perfect for building firewall filters, right? This is the exact type of thing you need to do, and this actually came out of our operational needs running a root server. It's like, we need to figure out now, if we should start dropping something, because it's actually going to affect us soon, what to do. So, piece of cake, thanks. So that's really the whole goal. It's like being able to get a very rapid understanding and build a tool that could actually tell us immediately. The hidden thing is there was a huge amount of increases to example.com. So let's go through some graphs of these. So there's also Taffy graph, which produces graph of like any value you want in the PCAP files that you're looking at. I'll note that actually these are all running on like 6 PCAPs. I run the graphs out of more than just the 2, because otherwise you get vertical breaks in them. Here's the unusual opcodes, right? You can see that the normal operation code of 0 is chugging along near 100%, and then all of a sudden we get all of these other opcodes just sort of storming in there. And you can see that the DDoS attack kind of trails off, and all the other opcodes kind of start falling away. This is the queries to example.com. www.example.com went up. Now, I don't know why, right? My best guess is that they run something else to check and see, are we still responding, right? So they're running a bunch of digs or something saying, hey, did we take them out? Did we take them out? Did we take them out, right? The interesting thing is that the example.com queries actually fall off a little bit faster than the DDoS queries. And I haven't gone back to do the correlations of addresses and things like that. Again, data set's actually available if you want anonymized data, but if you want to go play with it. I also looked at the truncation bit. So, not surprisingly, the truncation bit kicks in because, we're getting a lot of queries to one kind of thing, and you can see it, it mirrors. One of the things Taffy graph can do is compare percentages. So this is obviously, percentages from 0 to 100. Low truncation bit during regular times, and then it went up quite a bit during the attack. Now, I need help. This is the same time frame. Right? All the rest of the graphs you just looked at went up and then they went down. This is the same time frame. The checking disabled bit stayed high. Why? I don't know. I have not actually even run this graph for a longer period. I know eventually it's going to drop again, but I actually haven't done that graph yet, and I need to do that. But this one shocked me, right? When I threw this into the graph, I'm like, what? Why is it not falling off with the attack? What's causing that? And I have not figured that one out yet. So sometimes, tools give you more questions than answers, but at least it gives you something to look at, right? Otherwise, I would have not known to actually go look at this. So I will say that there are many, many more planned features that I have to throw into these. But again, my whole goal is to get you guys to give me features that might be helpful as well, so that I can prioritize that based on your needs. If that isn't a reason for you to go try alpha software, I don't know what is. I even have a UI that allows you to click and drag and explore and things like that. This is like the newest. It's even labeled pre-alpha up on the right. But you can do things like change the graph live and start clicking on different values and actually really start playing with the report characteristics and stuff as well. It has a detailed graph and like a total graph and then a browsable, scrollable thing full of all the reports. It's basically the same thing as Taffy of Taffy compare and Taffy graph combined into one tool. So my list of future things, and I'm not going to go into them all, is actually quite long. It's much longer than this slide. There are some speed and memory improvements that I want to do. I know that there's parts of code that are slow and parts that are good and fast. A lot of things I want to do just about helping you understand what portions might be the most helpful. I have a long ignore list. You really never want to know the TCP sequence number. It's just not something that you're going to really need to see most of the time. You can turn it off if you want. But I really want early adopters, and I really want your list to be on that right-hand side. I have a lot of general usage tips, and you'll see a documentation link on the very last slide. All of the usage tips are on the documentation page. There's actually a walkthrough of that last example I just showed also, so it tells you the exact commands to run and things like that. The one big one that I will say is always turn on caching. I didn't want to turn on caching by default because it creates fairly large, binary files right next to your PCAP file. So it's not on by default, but basically it really, really, really speeds up future runs. So you run any tool once, it caches a big amount of file, and then the next runs are a lot faster. There's different dissection levels, so the really fast ones are 2, and I just implemented 3 on a plane. Good story about that in a minute. And you can limit the number of packets so that you can actually speed things up if you're under real pressure in an operational environment. And I need to know now what the differences are. You can do a bunch of stuff to really help out with that. The rest of these I'll leave to look at the webpage, but do look at the usage tips because it's highly helpful. I will say that one of the things I learned how to do is split PCAPs into a bunch of pieces and process them all at once. You can very quickly chew through every CPU on your box. This is a 60-core 4 machine, running through some of the data. Do watch out for memory and CPU usage if other people are using the box, but it's actually pretty good. You give it n PCAPs and it will figure out how many cores you have and then try and use as many of those as it possibly can. So in the end, and this is going to be the end of my talk, is try it. Taffy is it's actually on my GitHub page too. I didn't link that up there, but you're welcome to file issues there too. I need to advertise that better. There's a read the docs page. I actually put a lot of work into the documentation for a fairly early version of a tool. It's easy to install and get up and running. And I would expect bugs. Again, it's alpha software. Okay, it might be beta. It might be good enough for beta, but do expect to email me if there's anything wrong. And a huge thanks to the Comcast Innovation Fund, who actually sponsored this work last year, and I'm super happy that they were able to. This is actually something I've been wanting to do for 2 or 3 years, and I just knew it was going to be a decent amount of work, so that when they were willing to sponsor the idea, I was all in. So it's far better than the bash scripts that we had, clubbed together that were running TCP dump and other stuff, and T-Shark underneath the hood and outputting boring ASCII. So. With that, thanks very much. Anybody have questions? And anybody get it installed yet? That's the real question. Excellent. Dwayne.
Hi, Dwayne Wessels from VeriSign. You were right, I did enjoy that very much. Thank you. So I have a few comments. I guess first one feature request is, how hard would it be to make it work with non-PCAP files? Is that an option?
That is on my list. Trivial, right? I tend to write very modular software in the first place. So right now it's taking in, PCAP, but internally it actually passes around a data structure with enumerations, period.
Okay.
So I know CBOR and things like that probably people are thinking about as well. Again, if you have a particular format you want, I can probably optimize that pretty darn quickly. So.
Yeah. One thing I expected to see on your feature list, I guess, was like automatic detection of the anomalous events. Is that something you're thinking about?
So we've thought about putting that into our operational detection mechanisms where you see a ramp of some kind. It's too expensive. So actually the lower level dissection levels, there's 10 dissection levels technically, but only 1, 2, 3, and 10 are implemented, 10 being really slow. You can't do 10 at line speed.
Yeah.
It's just too slow. You could do samples once every while. And then I have considered that.
Okay.
I haven't figured out how we're going to put it in, whether we're going to do edge detection on our graphs that we're creating or whether we're going to turn live. But.
Thanks. I'll let Stefan go. If there's time, I have one more question.
Okay. Definitely.
Stefan de Wink, SRDN. Thank you for the talk. I have not yet installed it yet. I wanted to listen to your talk, so I would suggest to update the slides to include the GitHub repo, so everyone who downloads the slides afterwards is pointed to that. That's all.
I actually have changed slides. OARC is very picky, rightfully so, and that's why the conference goes so well, is that they don't allow you to do stupid things at the very last minute. So yes, I actually have the slides already to update that fix the checking disabled bit.
But also include the GitHub repo in the update.
Yeah, and I'll include the GitHub repo as well. So yes, thanks.
Ben Schwartz, Meta. You asked for feature requests, I think. Yeah. So I have a feature request for you. So in November, the Beatles released a song. This was you might have seen the news. And the story is that John Lennon had written the song and recorded it with him singing over piano, but they couldn't, they needed to like separate those and potentially only use the vocals on the track. And so they needed a system that could take this single recording with both, with the mix of vocals and piano and split it. And so they were able to set up a system that could do that. That is what I want from this tool.
So no. So thank you actually very much. I don't know that I can handle piano and voice, but actually you brought up something that I meant to put on the slides that I didn't, which is not only do I want to be able to take different inputs, like Dwayne said, I have at least 3 algorithms in my head. Right now, this is all just statistical comparisons, right? Very, very basic. I have 2 other algorithms that we did for a 4-year-long intrusion detection project where we're actually looking for signals that suddenly come into correlation, because that's always an interesting thing. Like, it would have put example.com into correlation, with the checking disabled bit into correlation with these other ones. And that's where you really pull out low-level signals. So that's in my plans, and sort of flexible algorithms, to do FFTs or something else, is one way to do that.
Yeah, in this case, what I think that what I want is something that generates a decision tree that partitions the input into a pair of outputs where one of them is smoother than the input and the other one is more compactly supported than the input.
One of the things that I'm going to be doing for one of our other projects where we're labeling data sets is actually create a labeler, that will output, 5 tuples or something like that, and true and false values or something like that. But no, that's a good idea too. So. I also want to create automatic TCP dump filters, right? It's like you hit the gold, right? Here's the TCP dump line that you need in order to go start filtering, or IP tables or NF tables, or pick your firewall of choice. Dwayne,
do we have time for one more question? Okay. Yeah. So you had an example, the DDoS example, and example.com queries, and if I understood correctly, the example.com was not used as part of the DDoS. Those were separate sort of...
So I have not, this was literally like a week ago, and I was, concentrating on documentation and a bunch of other things, and I got, distracted. But I don't know, and I need to do source analysis to figure it out. The tools are not going to do everything for you. They give you the starting points for what a human should go look at. But I will say, to answer your question more succinctly, that the levels are very different. The example.com queries are 1/10 to 100th, somewhere in that range of the bigger. So I don't think it's part of the, I don't remember what the queries, so the queries were all like random garbage in most of the DNS packets. These were well-formed, DNS packets. So whether it was intentioning to contribute or whether it was a measuring system, I actually don't know.
Okay, yeah. Because it seems like it'd be interesting to identify packets or queries where it's www.example.com and the R code is weird, or like combine fields together and pull those up. But I don't think you're...
Well, one of the exporting things that I want will actually do that, so you can sort of look at a per packet basis. I detected these 5 things. Anything that has all 5 of them gets 100% score. Anything that has 4 gets 80% or something. So.
Relaying from Mattermost, John Todd of Quad 9 notes that in their systems, PCAPs don't see nearly as much as you might like, because they see a lot of encrypted traffic, and asks for a DNS tap support.
So there's actually a few things there. Some of the PCAP sniffing tools actually allow you to insert a key for, if you're running an HTTPS server. Again, this is not DNS-specific tool. It works for everything. And I've thought about that, and that's a good point. I think when we get to inserting other input sources, that we can do that as well. I will say some of the things in the tools aren't as well documented as I'd like yet, because they're dependent on other modules. So TLS, for example, is not decoded by default. There's a command line flag to say, please turn on, TLS decoding as well, and it will do that right now. But I actually don't know what modules, are default and which ones aren't in Scapy, which is the level 10 dissector that's so slow. slow but powerful. It does wonderful things like, one of my favorite reports that I got back that surprised me the first time is like, oh, your ICMP messages went up, and encoded in the header of the ICMP that got returned, it was a TCP packet, and inside the TCP packet, was an HTTP response, and so it actually goes to like multiple levels, and I'm like, well, that's a lot more than I was thinking I wanted. So they get really deep, and that's both good and bad. It's good for getting deep and understanding it, bad for speed. But yeah. All right. Thank you very much.